Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. My name is Nur Syahani binti Abdul Halim, AE1900045. I'm from Group 6, Section 4. We present you about the introduction from our project. Okay. For the first, in our project, a single phase input is consist type of electronic that in use this simulation model are rectifier, step down transformer, diode, PID controller, MOSFET, dual switch, LED light, and L-ion battery. The challenge that we threw is in using MATLAB software. And the objective, the aim of this project is to gain the knowledge in analyzing laptop battery adapter that consists of power electronic converter based on certain requirements, experience inspiration on performing the converter using an appropriate simulation tools, and identifying the issues or problems encountered, then propose a suitable solution.
A very good morning to all the lecturers who is watching this video presentation today. My name is Lee Jin Joy, and now I'm going to present you about the methodology part for our project about the laptop battery charger adapter. So first of all, let's look at the block diagram for it first. So first of all, connect the AC supply to a transformer. After that, we connect to a AC to DC converter, which should be a rectifier. After that, the charging will occur where it is connected to the lithium-ion battery, and also a voltage and current controller PI, and auto load switch is connected to here, and then the lithium battery will connect to the laptop while there's the discharging occurs. So next is about the working principle parts for the laptop battery charger. So the laptop charger will only function when it has AC current connected to it. After the current has applied to the current is passed through a transformer first to step down the higher voltage before enters to the AC-DC converter. So the function of AC-DC converter used to convert the current where from the input is AC to the DC for usage for the electronic part in the adapter and the charging part. So after this, it will continue with the charging process where the current will charge the lithium-ion battery, which will supply the current to the laptop for it functional. When the AC source is not supplied, the battery will discharge while supply the DC source to the laptop. So besides that, there will be voltage and current control PI and auto load switch to control the charging process, where it should slow down the charging speed when it's reached a certain amount of current has been charged, and stop when it's fully charged. Next is about the parameter of laptop battery charger simulation. Here we can see the parameter. The AC source is 220 volt, frequency is 50 Hz, step-up transformer is 240 to 28, capacitor 1 is 0.02 farad, laptop load should be 6 ohm, and resistor 1 is 5 milliohm, capacitor 2 is 1000 microfarad, resistor 2 is 5 milliohm, capacitor 3 is 5 millifarad. Nominal charging voltage is 19.2 volt, and also the rated capacity is 45 Ah as a parameter value. So that's all from my methodology parts. Thank you very much.
Good afternoon, my name is Suzy. My meeting number is AE19009. I'm from Group 6 and Section 4. Today, I'm going to talk about the design and analysis. Lastly, we combine the AC source to DC source converter design, DC source supply to the battery design, for charging or discharging voltage controller, current controller, and condition switch to become the simulated model of a laptop battery charging or discharging circuit. The simulated model of a laptop battery charger, which include an AC supply, step-down transformer, full wave rectifier diode, which there is TA1, T2, T3 and T4. Capacitor, resistor, ideal switch and MOSFET and a battery. The setup performance reduced the 220 supply voltage to 28 volts, providing the converter with an AC voltage of 28 volts. The charger output is coupled to the 90.2 volt battery. By charging the 90.2 battery converter, the AC voltage is converted to DC voltage and the DC current flow view the charging output. After setting the constant at 0 to open out the ideal switch means that the battery has been discharged and supplied to the battery. Besides that, the charging or discharging voltage and current are controlled by the controller PI, and lastly, the condition auto lock switch is controlled by the constant. So this is all for me. Thank you.
My name is Daniel Ganifat, AE19007. Today I'm going to do a presentation on a single source AC to DC converter for the laptop battery adapter for the group project Power Electronic BEV30203. So over here in my simulation, I am using a Power GUI with a discrete and a TBE solver and an AC voltage of 220 volts and 50 Hz frequency. So I'm going to step down using a linear transformer from a 220 to 28 volts. So for my battery, I'm using this 19.2 nominal voltage and a 45 ampere hour. And for my initial state of charge, I'm using 70. So for my AC to DC, I'm using 4 diode, which is a full wave rectifier diode with a capacitor filtering. The purpose of using this capacitor filtering is to smooth my the oscillating waveform from a AC to DC converter. So over here, I can show you that I'm using this to convert my full wave rectifier output waveform to this, so that it will become more smoother. If not, the oscillating waveform will get huge. So as you can see here, I'm demonstrating 5 seconds of oscillating waveform from an AC. Left hand side is AC, this one is DC converted. So I just stop here. So as you can see, this one is with the capacitor filtering, it's really smooth compared to the left hand side AC. Okay. Over here, I have a main switch over here and a dual MOSFET switch, and I'm using my load with 6 ohms, and then there's a RC series branch and RL. So this is the main switch. When I'm giving it to 1, it's going to charge. So as you can see here, the battery is going to charge. Okay, it's going to charge, and the state of charge is increasing, and the waveform of the voltage and the laptop load voltage is around 25 to 27 like that, and then the current will be charging in a negative 3 ampere. Okay, the negative because it's charging, and when I'm using this discharge waveform, as you can see here, when the battery is low, I'm using it for a discharge waveform. So when I change to 0, it's going to discharge. So this one switch is open, and we're not using here. So it's using the battery to supply the laptop load. As you can see, okay. Okay, you can see it's using the laptop load. Okay, so the laptop usage currents is all like 7.5 ampere, and laptop load voltage using is a 28 like that. Yes, and for my voltage for the battery, it's supplying using 20.7. So as you can see over here, it's discharging. Yes, we are using the battery, so the step charge will be dropping. Okay, and over here I have a current controller, which I'm using the PI controller, And we have a charging voltage controller. This is also a PI as well. And for this charging, it's also, and this is a switch, auto lock switch. So I'm going to use it to control using this 0 and 1. That's it for my presentation. Thank you.
And a very good day to our lecturer. My name is Punchun Phai with the matrix number AE190091 from Group 6 of Section 4. In my segments of the video, I shall be presenting the results and discussion part and also the conclusion. Now I shall give a brief presentation on the results and discussions. Starting from the charging situation, since this is the charging duration from figure 4.1 and 4.2, they are basically the same thing, only one is zoomed in and the other one is more zoomed out. So we were able to deduce that the AC-DC converter of the laptop battery adapter is working as we intended by analyzing the graphs in these figures. We have AC voltage graph on the left, which is oscillating at 220 volts peak voltage and 50 Hz frequency, as shown here at the left side. Then we have the DC voltage, which is at the right side, which is DC voltage, which is rectified from the AC voltage and is oscillating between 22 volts and 28 volts at a stable condition in the positive cycle region, but never in the negative cycle region. The filter capacitor in the full wave rectifier circuit has done its function in suiting the graph waveform of the converted DC voltage to a better result and stabilize the entire voltage in the laptop load and battery. From figure 4.3, we were able to acquire more information about the laptop battery adapter and laptop model that has been implemented in MATLAB Simulink. On the upper left corner, we have the state of charge, or SOC, and it is very apparent that the laptop battery is being charged by the input source as the line increases linearly across the graphs at from 46.7%. Next, on the upper right corner, we have the voltage of the battery, which is stabilized at about 20.8 volts if we zoom in over here, after an initial rise of voltage at the beginning as seen from the graph. Now over to the lower left corner, we have two elements. One is the current of the battery and the other one is the laptop usage current, which are being denoted by the blue and red line respectively. From the graph, we observe that the battery's current stabilized at around between negative 12.5 amps and negative 4.5 amps, whilst the laptop usage current has stabilized at around the red color here at about negative 13.5 amps, and the negative sign convention is present, as you can see over here, is because due to the charging of the battery. Finally, at the lower right corner, we have the laptop load voltage, and we have observed that the voltage has stabilized between 22 volts to 28 volts over here, as you can see, the blue line, which is similar to the value of DC voltage that we have acquired earlier. Alright, now we are at the discharging situation. So from figure 4.4 and 4.5, we were able to see that the laptop is being powered by the battery, as evident from the graph. On the left, the AC voltage never changed, and it is still 220 volts peak voltage and 50 Hz. On the right, however, the DC voltage graph is different from the one in figure 4.1 and 4.2 earlier, as the DC voltage's oscillation is quite widespread during the beginning. But as the simulation progresses, it stabilized and started oscillating between 26 volts and 30 volts. This is the same graph, but it's a bit zoomed in than the figure in 4.4. So yeah, as you can see over here, this is DC voltage, this is the AC voltage. So now I shall give a brief explanation on figure 4.6 as well. From figure 4.6, we were able to observe how the battery becomes the power source for the laptop instead of the AC power source. On the upper left corner, we have the state of charge, or SOC, decreasing linearly from 46.7% due to the fact that the battery is discharging by powering the laptop. Next, on the upper right corner, we can observe the graph of the battery's voltage. It started out erratic from the beginning over here, but stabilized at about 20.6 volts, which is only a little lower than the value of 20.8 volt that we have acquired when the laptop is being powered by AC power. Hence, the discrepancies between the two values were not too vast or too different. Afterwards, on the lower left corner, we have two elements again. One is the current of the battery, and the other one is the laptop usage current, as they are being denoted by the blue and red line respectively again. From the graph, we can see that the current of the battery is stabilizing and oscillating between 5 amps and 8 amps, whilst the laptop usage current has stabilized and oscillating between 6 amps and 7 amps. And a positive sign convention, as you can see at the left side of the graph, indicates that this is the discharging of the battery, since the battery and the capacitor to discharge and supply the current to the laptop load. And lastly, on the lower right corner, we have the laptop load voltage, and we have observed that the voltage has stabilized at around 26 volts to 30 volts over here. As you can see, it started out quite erratic, but it stabilized as the simulation progresses. And the voltage that we found, which is 26 volts to 30 volts, is similar to the value of the DC voltage that we have acquired earlier with figure 4.4 and 4.5. Okay, I believe that is all for results and discussions. Thank you. Hello, it's Punchin Fa again, and finally we have come to the conclusion. As a conclusion, we were able to learn the inner workings of an AC-DC converter with a laptop battery adapter through the utilization of the software simulation of MATLAB Simulink, and observe how AC power is being used to power a device that uses DC power, and at the same time the laptop's battery is being charged. In addition to that, we also learned how the battery for the laptop would power the laptop whenever AC power is unavailable or removed. From the observations that we have acquired, we can see that the laptop battery adapter, which is an AC-DC converter, is crucial in powering the laptop and charging the battery. Without the right and proper AC-DC converter, the laptop simply would not work as intended, and the battery would be damaged due to excessive amounts of electricity. During typical use of a rechargeable battery, the positive electrode's potential remains greater than the negative electrode's potential in both the discharge and recharge. During the discharge charge cycle, however, the role of each electrode is shifted. When discharging, the positive is a cathode, whereas the negative is an anode. When charging, the positive is an anode and the negative is a cathode. Last but not least, from the graphs that we have gathered, we can see that whenever either the laptop is powered by an AC or the DC power source, the elements that we have observed upon do not deviate much from one another, except for the state of charge, or SOC, as that indicates the charging and discharging of the battery. That is all from us. Thank you very much for watching the video.